functions, right? For these functions, E, H, A, S, G. So there are two types of departure function depending on whether the temperature and volume is specified or the temperature and pressure is specified. So any one of these can be called as U. So we look at two different departure functions. Of course, for U equal to E and H, the two are equal. The two departure functions are equal. We saw the reason for that is that the ideal gas internal energy as well as the ideal gas enthalpy is independent of volume or pressure and depends only on temperature. On the other hand, for all of these other three functions, the entropy, specific entropy, the specific Helmholtz free energy and the specific Gibbs free energy, the two departure functions will be different and you have to take that into account. So what we saw was whether temperature and pressure are specified or temperature and volume is specified, you would have to, if temperature and pressure is specified, you still have to determine the volume at that state. So what you can do is you have to verify that all of these departure functions can be calculated provided the equation of state is given. Formula might differ from one to another, right? But you can easily verify the only input to calculating these departure functions is the equation of state, which we assume is given to us in this form. Pressure expressed as a function of the specific volume and temperature. Right? So once we are given this, given a temperature and pressure formula, you will see that even for this, have V1 will appear in the formula. Right? So that V1 corresponds to the given temperature and pressure of the actual substance. Right? So V1 is sort of defined by this relation as to satisfy the equation of state of the actual substance. Right? So that is the important point. So we have to find the volume, specific volume corresponding to the given temperature and pressure. Of course, if the V1 and V1 are specific, you are directly given that. It's in fact easier to calculate the pressure in that case, if at all it is needed. So now, based on these departure functions, I can define, especially the G, define what is called the fugacity of a pure component. So function of temperature and pressure. The fugacity is defined as, define it like this, because we know for a homogeneous, a pure component, G is actually equal to the chemical potential. So typically it is defined using the chemical potential. The pure component is the same as the Gibbs, specific Gibbs free energy. Some formula is pressure times the exponential defined as the product of the pressure times the exponential of this departure function of the chemical potential evaluated at the given temperature and pressure. So if we want to calculate the fugacity temperature and pressure, I would have to go to the departure function for either the chemical potential or the specific Gibbs free energy to calculate that departure function at that temperature and pressure that is specified. Divide that by RT, take the exponential of that and multiply by the pressure. So clearly this you can easily verify as the units of energy per mole. And this is units of energy per mole per Kelvin multiplied by temperature. So units are consistent because when you take exponential, it's important to check whether the what is within the exponential is what are the dimensions, right? It's clearly dimensionless. So the dimension of the numerator and denominator are the same. However, pre-multiplying that exponential is the pressure of the state, actual state of the substance. So clearly, what are the units of the fugacity? The pressure. So it's very important. Whatever units you use to, this of course has to be consistent. Joule or kilo, joule or whatever. This, the units of the fugacity will be determined by what units you choose to express the pressure in terms of. Right? So it has the same units as the pressure. Note of caution, since we know is not equal to, because you have two formula I wrote down. One which calculates the departure function given T and P is specified, and one where the T and P is specified. There are some terms, additional terms that come in the T and P. That has to be used to calculate the fugacity, not the one involving T and B. Right? So that's very important. This is the departure function of the chemical potential at the given temperature and pressure. That's what is important. So same units as pressure. Now you can see that we have earlier seen that the ideal gas chemical potential can be expressed like this. Some function of temperature plus RT times logarithm of P. Right? So at low pressures, the ideal gas chemical potential blows up. Right? Now since any substance, the actual substance also behaves like the ideal gas. Right? At sufficiently low pressure, you will expect that for the actual substance also at very low pressure, the chemical potential will have a very large negative value, typically. So you're doing calculations involving the chemical potential at very low pressure, you will have to deal with very large numbers. But you can see, this is one of the motivations for introducing the fugacity, right? But you can see as T goes to 0, U or goes to minus infinity. However, what happens as P goes to 0 of the fugacity? Right? Or rather, you can say P goes to 0 of the ratio F over P. Actually, because as the pressure goes to 0, these two become the same. The exponential of 0 will be 1. So the ratio F over P goes to 1. So the pressure at low pressure, so you go to sufficiently low pressure, the fugacity will effectively become equal to the pressure, right? Or more or less. In the limit, they become the same. But at low pressures, when you're calculating the fugacity rather than the chemical potential directly, because the fugacity has a difference of the chemical potential and the of the actual substance and the ideal gas associated with that substance. So the difference would make the fugacity actually, it will not blow up at low pressures. It will tend towards the pressure. So, since fugacity has the units of pressure, these are all the reasons why the fugacity, in actual calculations, you are better off dealing with the fugacity and then work backwards and calculate the chemical potential if needed. Right? You're better off dealing with the fugacity rather than the chemical potential directly. Right? Because of these vastly different limiting features at low pressures. Another way of looking at this is that since at low pressures, that is the ideal gas limit, the fugacity of the actual substance tends towards the pressure, right? So you can regard the ratio F over P in general at all pressures as representing the value of that, as representing the deviation from the ideal gas behavior. We see through numerical examples what values F over certainly will be. The more it is different from unity, it is very. Let's say you calculate the fugacity using this formula, right, and you find that the fugacity is very close to the given pressure. That means you can say that the substance is more or less behaving like the ideal gas. It is sufficiently low pressure, we don't know what is sufficiently low for each substance. Right? So what is low for one substance may not be for another substance. It also depends on the temperature. Right? So if you calculate the fugacity and find that it is more or less matching with the pressure, then you can say that the substance is behaving like an ideal gas. Right? And so we define a new quantity. It is the ratio of the fugacity to the pressure. That is called as the fugacity coefficient. If the fugacity coefficient is close to 1, then the actual substance behaves like the ideal gas. Limit p equal to 0 of phi is actually 1. By calculating the fugacity coefficient, we can determine how far the actual substance is from its ideal gas behavior. Right? So that is the motivation for another important significance of the fugacity. It gives with just one number how much a measure of the deviation from the ideal gas behavior. Are there any questions on the definition of fugacity? We'll make use of the fugacity repeatedly later. Right? But for now, I'm just introducing the definition. We'll move on from here. Right? So the definition is clear. Then we will move on to the actual purpose of introducing the behaviour function itself is to calculate the change in go back to that problem. If we started with that problem, we chose different parts, and then we said that as long as we are in the gas phase, it's easier to work with the departure function and calculate the departure function, because that requires only the equation of state as the input. So we separate this calculation of the change between two equilibrium states of any property into two parts. We divide the calculation of delta U into two parts. One which will involve the calculation of the difference in the departure function corresponding to the two states, whereas one that would involve only the ideal gas property. That's easy to handle. Right? So this is indirectly adopting the part C that we took, calculating the difference in property between any two states. That we go through the ideal gas state. That is, so we then separate, and it's more easier to look at it in two parts. And if you look at the formula for delta U that we go to for part C, we will have both the specific heat and the equation of state part. So convenience dictates that we separate it into two parts. In one part, the equation of state alone is the input, so I handle it separately. The other part would involve the ideal gas properties. Right? So now that I have established the formula for the departure function in both the temperature pressure as well as the temperature volume domain, depending on the specification. So if I know how to calculate the, let's say T1 and P1 are specified, and then we're going to T2 and P2. So the formula that you have, so this is really U minus UIG, T2, P2 minus P1. That's what it means, the delta, that's what it signifies. So I know all the formula that we have given involves P1 and P1, and of course P1 also would come in, right? So if I want to calculate it at some temperature T2 and P2, wherever T1, P1 appears, I have to put T2 and P2, and wherever P1 appears, I have to calculate the specific volume corresponding to T2 and P2 and substitute that. So if I know how to calculate the departure function at one state, I know how to calculate it at any other state. The same formula will apply. Right? So I know how to calculate this now. In principle, at least, given an equation. Now we will look at how to calculate this for all these 5 properties. Formulas are very simple. It depends on well-known properties of the equation, the ideal gas properties, right? So let's look at that very briefly. And first again we'll take the E, the internal energy. What I mean by delta EIG, and look at again both temperature and pressure are specified, or the temperature and volume are specified. The internal energy and enthalpy do not matter. Right? So this, what I mean is evaluated at T2, P2. So now I am assuming that the T2 and P2 always correspond to the state of the actual substance. So for that state, I want the ideal gas property. Right? Minus, this is what I mean. If T and P are specified, this is what the delta EIG or epsilon EIG would mean. Now, we know that the internal energy is independent of the pressure, so I can write this as T2. So it's only the temperature that will determine. Right? So if you involve a change, you have a change of state of the actual substance, right? That involves no change in temperature. That's a special case of the changes we have considered. Then the corresponding internal energy change for the ideal gas will be zero. And this can clearly be written as an integral as T1 to T2 Cv, which is, can in general be a function of temperature. Or if you take the view, since tables actually give the Cp of the ideal gas, right? So if we want to now express everything in terms of Cp, then we know that for the ideal gas, Cp minus Cp is a constant and equal to the U. This is per mole specific heat that you have to keep in mind. So this can be written as C1 to T2 Cp Ig, which of course will be a function of temperature minus R dE. This can then be written as T1 to T2 Cp minus R times T2 minus T1. Now on the other hand, if I specify the state through T and B, right, then you can easily see that, so this is I would call this TB. Now delta is EIG T2 B2 minus, that is the same as this, because anyway the internal energy is a function of the temperature of the ideal gas, right? So it doesn't matter whether I specify the change of state of the actual substance in terms of T and B or T and B. This change of the ideal gas specific internal energy is not going to change. So I get the same formula. Same principle will apply for the specific enthalpy. If I take that now, I can easily write that as, which is actually HIG, which is of course given just by T1 to T2 CPIG. Now of course if the specific heats, let's say over the temperature range, right, the specific heats are not varying that much, then we can replace it by some average specific heat, right, and I can write this as some, similarly you can write this also in a similar way, but that is a special case where there is not a significant change in the specific heat over the temperature range I am interested in, right? To a few hundred degrees, it might not vary that much. You have to check that. Then I can replace it by some average value, or a good approximation could be I calculate the Cp at T1 and at T2, take the arithmetic average, let's say, and then use that as some approximate. This is only an approximation. Same way I can write an approximate formula there also. But in general, what you have to remember is in general the Cp is a function of temperature. So if I give you a temperature dependence of Cp in the exam, you should make use of that and calculate the whole integral and do it. And you cannot simply say, I assume some constant value, right? That is only an approximate formula. For lack of data, whatever, we can use that, right? Or for instance, I give you only one CP value. I might not mention anything, assume it to be a constant. For lack of any other data, you can take that value and calculate the changes, right? So this is for internal energy and enthalpy. Now, what about the other quantities? Entropy is slightly more involved because the entropy of the ideal gas is function of both temperature and pressure, and as a result, the change will depend on whether T and P is specified or T and B is specified. Let's now do that, and let's first take where T and P are specified. So we have to write this as an integral, right? How would you write it as an integral? Integral, let's say 1 to 2, what would be within the integral? ds by dt times dt plus ds by dp times dp. So you have to choose a path, but for the ideal gas it is made very simple. We will see now. So I can write this as this is a fixed pressure. That's what I have. Between the two states T1 and T2, which are T1, P1 and T2, P2. Now ds, the derivative of entropy with respect to temperature, constant pressure, what is that? Cp by T, that's important. Now a T would come in the denominator. So that Cp I know is a function of temperature alone. So what you get is that the term involving the dt, that ds by dt is a function of temperature alone. So it sort of separates out nicely for the ideal gas. Otherwise I have to choose a suitable path and maybe split it into a constant temperature path and a constant pressure path. That's not really needed here. So I write this as T1 to T2. Of course, again, Cp is approximately constant, then I get Cp times logarithm of T2 by T1 here, right? Because I have a 1 over T in the denominator. Now, what is ds by dp for the ideal gas? And ds by dp, two important Maxwell's relation you should try to remember. ds by dp is dp by dt for any substance. ds by dp is minus dv by dt. So for the ideal gas that would be minus integral p1 to p2 r over p dp. This of course can be easily written as r logarithm of p2 by p1. And that can be integrated because r is a constant, universal gas constant. So I can integrate that and give the final form. Of course, if I want, if this is a constant also, then I can maybe write it as, to give a closed form, minus r ln logarithm of p2 by something like that. Now you will see that if I want to if rather the state specification is in terms of T and B, which is usually not the case, but we need to be able to handle that as well, right? So what you have to understand what I mean by this. What I am saying is, I'm giving you a change of state of the actual substance, and I say that it changes from a temperature T2 and a specific volume V2 to a temperature T1 and a specific volume V1. So clearly in that case, I would go to the departure function which expresses the departure function in terms of T and P specification and calculate the difference. Then I will come here. Since T and P are specified, I will use this formula for the ideal gas. Now this is again 1 to 2 is. This is very important here. This is now a constant volume and not a constant pressure. And again, this derivative with respect to temperature is also at V. Again, you will see there will be a good separation of the two integrals. Otherwise, the integral is coupled, right? And so ds by dt constant volume is Cv by T. So that would be integral T1 to T2 Cv Ig by dt. Right? And this is dP by dt, which for the ideal gas will become R over P. And so that would be plus R logarithm of V2 by V1. Now, however, if you want to express it in terms of the Cp, that can also be done. So this would be Cp integral V1 to V2 minus R, that is minus R over T, right? That would be minus R logarithm T2 by V1 plus R logarithm V2 by V1. Of course, you can combine the two and write this as plus R log V2 by V1, right? So times T1 by T2. Now, are these two the same or are they different? The actual substance, not of the ideal gas. That's very important, right? Because on the face of it, because I know that dV by d is a constant for the ideal gas, so I can certainly probably replace this by V1 by V2 or something, and then it look as if the two formula are the same, but they are not, because you are not allowed to do this. The V2 and V1 that I introduced are by our notation corresponding to the pressures of the actual substance, not of the ideal gas, right? They have to be careful in doing that, right? So that is something that you have to keep in mind. This is a recurring problem we have had earlier. What I am saying is that if I want to write this V2 T1, right? I can write this in this way: Ig V by D is a constant, right? So Big 2 T2 by T2 is Big 1 B1 by B1. So from that B2 by B1 times T1 by T2 is actually P1 Ig by P2 Ig. That is fine. So it is correct. I can write this in terms of minus R log P1 by P2 of the ideal gas, but I don't gain anything. It's in fact confusing. I'm deliberately letting it convey to make a point, right? Because whenever I write P1, this is the P1 and P2 of the actual substance. But here, T, B, and T2, P2, and T1, P1 as because I have to go and find the actual pressure and of the substance of the states at 1 and 2. Right? That will clearly not satisfy this relation. Right? So you have to be very clear. And I don't gain anything by writing it in this way because V1, T1 and V2, T2 are what are given to me as specification. So I want to express the change undergone by the corresponding ID gas in terms of those and not unnecessarily going in the pressure. Question is given T1, V1 and T2, V2. Can I estimate the change due to the ID gas because I am looking at this part? Yes, I can. Right? If rather T1 and T2, P2 is specified, then I go to this formula and calculate it. Everything there is expressed in terms of T1, P1, T2, P2. Right? So that's what you have to understand. I don't have to bring in P1 there. In the same way, I don't have to bring in P1 and P2 here. That's something you have to keep in mind. Now the other two quantities, A and G, you will find that they will involve some value of the entropy at a particular state, and I just explained that with A. But we want to calculate AIG, let's say T2 minus AIG at T1. Now I can approach it directly in terms of the derivative of A with respect to T and P. But rather, since I have already got E and S, right, I am making use of the fact this is EIG at T2 P2 minus T2 SIG at T2 P2. Because that is what it is. A is defined as E minus TS. If I want to evaluate the ID gas at T2, P2, then I can, if I know the internal energy evaluated at T2 and P2, of course it's dependent only on T2, I'm just writing it for the sake of the completeness. And then I have it's very important to put the correct temperatures. Because in the first term, it is T2, E minus Ts would involve T2. The second, this is what will complicate the formula slightly because you cannot really write it as a difference of the entropies, right? So now, this is straightforward. This is E that I already know, it depends only on the temperature. So I can write this as Cv. If you want, you can further write it as a term of Cp. But now, here if you see, I cannot really write it as SIG T2 P2 minus SIG T1 P1 because each one of them has a different factor multiplier, right? So I would have to sort of leave it as, I can for instance write this as but I can remove, so I need actually the values of the entropies of the ID gas at the given temperature and pressure. So that you have to go back to the formula that we derived while deriving the various fundamental equations for the ID gas, right? We can easily get an expression for S in terms of T and P. So we need to be given that, otherwise I cannot calculate this. However, I can simplify it slightly by expressing the ideal gas entropy at T2, T2 in terms of the ideal gas entropy at T1, P1 by choosing a certain path. For instance, now suppose I have this, let's say this is P1, P1 and let's say this is P2, P2. So I can choose our famous path A, let's say. So I can write this as SIG P2 T2 minus SIG. So I'm going to express it. This is not what I have here because I have T2 and T1, but I can get a slightly more simplified formula so that only the value of entropy at one temperature is there in the final formula. I'll leave it for you completely, but I'll write this as SIG, I call this state A minus SA plus SA what is SIT P2 minus SA? A is actually given by a pressure P2 and a temperature P1. Right? So A is actually the state SAIG is of P2 P1. So how would you calculate that? P2 P1, P2 P2 minus P1 P. What is that? Integral dSIG by dt. This is only a dSIG by dt. Of course, S depends on both temperature and pressure for the ideal gas. But ds by dt for the ideal gas is a function only of temperature. Right? So I don't even have to specify the P2. For common substance, for a real substance, I have to specify what pressure that is calculated. So this will be from T1 to T2. dt. This is actually CPIG by T. Right? And then what about that? This is integral. This will now be P1, P2. So ds by dP will come into play. I want you to think along those lines rather than trying to remember some formula. Right? Very clearly, this temperature is fixed. So the only quantity that will come into play is ds by dP. That is R over P minus R over P for the ideal gas. Minus R logarithm of what I can do, I'll get you to get the proper expression. I can take this and write this as this is equal to, that is actually this SIG at T1 P1, right, plus all of that. So I can take that, take this whole thing and substitute for, so I can express everything. So it will be a somewhat long-winded formula. So the input now, apart from the Cp of the ideal gas, everything else, right, you can determine once the Cp is given, which is given in tables. But here, on top of it, you will find that I also need to be provided the actual expression for the entropy, not just its derivative, the actual expression for the entropy in terms of temperature and pressure. And given T1 and P1, or at least give the value of the entropy of the ideal gas for that substance at a particular temperature and pressure. So the whole formula, apart from Cp, will also depend on a particular value of the entropy of the ideal gas at T1, P1. So I can sort of simplify and remove this dependence on both, because the two are related. Right? So I'll let you, I'll maybe give it as an exercise, and you can easily show what the final form would verify what the final find out what the final form would be. So clearly AIG T2 P2 minus, you can easily expect that again this will not be equal even for the ideal gas, right? So that will involve some changes, and then another other two quantities I am not going to write down. And similarly for T1, P1, this again can be after once you have that, because P is simply A plus PP, I can easily get the difference. Because PP I know for the ideal gas is simply RT. So that's just going to give a quantity. The change is going to simply give R times T2 minus T1. So whatever once I have, so I can easily from this write this as A so I have A plus PB is G, and PB is RT for the ideal gas. So clearly this will be R times T2 minus T1. So the Gibbs free energy change, similar formula will hold for T2, V2 minus T1, V1 would be AIT T2, V2 minus AIT T1, V1 plus again R times T2 minus T1. But that term PV is dependent actually only on temperature and not on, can be expressed rather in terms of temperature alone for the ideal gas. So that is going to give that. So they sort of completed the entire cycle of calculation, that is got the formula in place. It's taken this long because to do any calculation involving change of state, we have to assemble all this information. Now, right, so what are the inputs? The inputs are the equation of state of the actual substance, which will determine the change in the departure function. And what are the inputs for the change in the ideal gas property? Certainly this would sufficient for the internal energy, enthalpy and entropy, but for A and G we would in turn need the entropy of the ideal gas at some given temperature and pressure. Right? That is very important. Now let us give it at some T0, P0, arbitrary temperature and pressure. You can certainly use the same idea to calculate the entropy at the P2, T2 and P1, T1 in terms of that. So that is an additional quantity that I need. Right? So are there any questions? Right? We still have a couple of minutes left. And so what I want to do is to now give some specific instances where the changes in properties would actually have significance. This is a standard simplified situation somewhat, except one or two. Right? And encounter them widely in actual practice, but please give the physical significance of some of these properties. We have already pointed out that from the general first law of thermodynamics, which applies for reversible as well as irreversible processes, which is a change in internal energy between two states, is a net heat input to the body minus the work done by the body. Now this is true for both reversible and irreversible. Now if I take the adiabatic, we have already seen this, I gave this as a motivation. But adiabatic, which means Q is 0 throughout, there is no heat input at all, the net heat is also 0 minus W, which would mean that W is actually minus delta E. So, now what is the relevance of this to the whatever we have carried out? We have seen certainly how to calculate delta of any property E. If we are given this is for a fixed amount of fluid, so if we calculate the delta for small e or the epsilon, I can easily calculate this. Right? Now the only assumption here is that undergoing the process, it might be reversible or irreversible, whatever it might be, the details of the processes are not here important, but important that the starting state and the ending state are both equilibrium states. So without any reference to what is happening in between, I can calculate the work done in the process. This is very important. This is of course only for adiabatic process. If you consider non-adiabatic, you have to somehow give the heat input. Now a sort of analog of this, where you calculate the heat, or you can relate the heat to the entropy change, is of course there I have to, this is the first example. Second example is a reversible process, the body undergoing a reversible process but constant temperature. Right? So now we know that ds by dt for a reversible process, equality holds. Right? This is a very general way of writing it. And later we brought in the time so that you can clearly see how the constant temperature will simplify. Our constant temperature, dS by dt, is simply 1 over T, integrating T1 to T2 QR dt. Now what is this? By evaporation, equal to T2 QR dt. Otherwise the temperature is inside the intake. The temperature is changing. I cannot take the temperature out of the intake. Constant temperature process. And again the equality holds only for reversible. Otherwise I have to make it unequal. What can you say about QR dt from T1 to T2? In terms of quantities that are written there on the board, what can I equate it to? What does it represent to you? The net heat input to the body over the process. So I can write this as 2 over T. So T is a constant temperature. So I can easily integrate this now and write this as, right, if I bring it over here, the T over here, I can leave it there itself. I can very easily show that Q is T times delta S. Qualification. So what is the qualification here? Adiabatic. Adiabatic process doesn't matter whether it's reversible or irreversible. The work done is negative of the internal energy change. That is valid whether the starting and ending states or equilibrium states are not. However, if it is true that the starting and ending states are equilibrium states, then I can use all the formula that I have derived. Right? So you remember all these qualifications. Right? Now here though, the qualifications are constant temperature plus reversible. Then the change in entropy, right, will give the net heat absorbed or emitted or whatever heat interaction divided by, the heat will be given by the temperature times the change in entropy. Right? So here again we assume that the ending and beginning states are equilibrium states. So I can use the formula that I have developed for the change in entropy to calculate the heat interaction, but in this special type of process. We give other examples for the Helmholtz free energy, enthalpy, and so on tomorrow's class.